Hi, folks. Happy Saturday. Hope you're all having a nice weekend so far. So in this video, I just want to address some trigonometry problems that one of my students was having trouble with. So these were problems that my student particularly selected and asked for a little bit of help with. So our first problem we have, I think there's just three we're going to be doing in this video. The first out of three would be graphing this function, this trig function. So the parent function here would be secant of x. It's always a really good idea to identify the parent function first, because that way it gives us a good idea of what we can expect this thing to look like. So this is the secant function. So what I like to do in a problem like this is identify what the parent function looks like when we graph it, and then that'll help us understand what our final result should look like. So you guys may not remember what secant looks like. So when I was first learning trig, I always put this in terms of cosine, because there was one of those reciprocal identities that tell us that 1 over cosine equals secant. So I want to draw cosine first. So I'm going to draw one period of the cosine function. And I'm going to do my best. By this point, you know not to expect that much from my drawings, but I will try my best. So cosine is going to look like this. This is going to be one period of the cosine function, just the standard cosine without any modifications whatsoever. So we start right here at 0, 1. It consists of an all the way down and then an all the way back up. So that's how we know what cosine looks like. So secant is going to be the reciprocal of cosine. So I'm going to use a different color to draw what a secant looks like based on cosine. And then I want to identify all the reciprocals, because, well, cosine doesn't have any reciprocals. Secant will have reciprocals. And the reason for that is because secant can be written like this. Secant can be written as 1 over cosine of x. So because we have a fraction situation, we can't have a 0 in the denominator. So we want to ask ourselves, for which values would cosine be 0? That would be everywhere we have pi over 2 or a 3 pi over 2. So that would be right here would be one asymptote. Here, I want to use maybe the skinny line for this one, for the asymptotes. So it should be the place where the cosine intercepts the x-axis. So these would be the two vertical asymptotes we have in one period of our function. And like I said, a period consists of an all the way down and then an all the way up. This is just one single period. So these are the asymptotes. They are the zeros for cosine, which turn out to be the asymptotes for the reciprocal of cosine. They turn out to be the asymptotes for the secant function. So let's go ahead and continue drawing this thing. So this is what the parent function looks like. And then we're going to use this to help us figure out what this should look like when we graph the function that we're given in this problem. So that's the parent function. I'm going to erase cosine because we don't need that part anymore. But I think I do want to keep the asymptotes there. So that's what our function looks like in a sense. So let's talk about what all of these modifications do. So let's talk about what happens on the inside of the function first. We call this the argument of the function. The argument of the function is always going to be the thing we plug in. So x times pi over 3 is going to be the argument of the secant function. So everything that happens on the inside affects the x. Everything that happens on the outside affects the y. So the -2 affects the y values only. Everything on the inside affects only the x values. So if it were just secant of x, it would look like this. But we have pi over 3 secant of pi over 3x. So let's talk a bit about what that does. So ordinarily, we have points of interest at multiples of pi, or maybe at multiples of pi over 2. So what happens when we have an x value times pi over 3, it means points of interest are going to be not in terms of pi. Give me a quick second. I think someone's calling. All right, my apologies. It's really unprofessional. I know. I'm sorry about that. So hopefully I can continue now without any interruptions. So like I was saying before, these asymptotes apply to the parent function, but not to the one we're given. So we want to modify this so that it applies specifically to this function that we are given to graph. So our points of interest, like I said before, usually are in terms of some multiple of pi or in some multiple of pi over 2, but because we have pi x over 3, the points of interest are not going to be in terms of pi. So because we have pi x over 3, our first vertical asymptote is going to actually be at x is 1/2. So instead of this being pi over 2, this is simply just going to be 1/2 for our first vertical asymptote, and I'll type that. That's our first vertical asymptote. And then the second vertical asymptote, instead of it being as 3 pi over 2, it's actually just going to be 3/2. We're not going to have the pi there. So here we have our two vertical asymptotes. So we finished in terms of what happens on the inside. So like I said before, what happens on the inside of this function affects the x values. What happens on the outside of the secant function affects the y values. So we've taken care of all the x values. Now we need to consider how this -2 out front affects the y values of the function. So if it were just +2, the 2 would have a vertical stretch by a factor of 2. So I'm going to use a different color to show how it affects the way the graph looks. So instead of looking like this, it would look something kind of like this. It would stretch the graph vertically by the power of 2. It would stretch it up and down. Imagine you have a rubber band. So this right here would be the rubber band in normal form, and then imagine you stretch that rubber band. So I think I might actually, I don't know if this is a good analogy or not, but I'm going to try my best. So imagine this is your rubber band just sitting there unstretched. So then imagine you stretch the rubber band out, up and down a little bit. So I'm going to show you what that looks like. So imagine that we're stretching that rubber band out. So when we stretch the rubber band, not only do we increase the height, but notice how it gets skinnier and skinnier. We're making it tight, we're making it taut. That's why this rubber band looks skinnier than the red one. We stretch it out, it gets skinnier, it gets longer. So I'm not sure if that's a good analogy at all, but that's kind of what I use to help me understand what's really happening in this problem. So we have this rubber band, we're stretching it out. So that's why it stretches outward like that compared to the original. And that's why the same thing applies when we're going down here and when we're looking at this part of the graph too. We're stretching it out by a factor of 2. But then we also have that negative out front to worry about. So the negative out front, we consider that to be a vertical reflection. So we're going to be reflecting this graph across the x-axis. So let's consider what that means for a second. So if this point right here has coordinates 0, 1, that means when we modify the graph and make it negative, we're actually going to have a point instead at 0, -1. So I'm going to use a different color to identify the final result. So I think I'm going to make it green. So the final result would look like this after we apply all of those transformations. The asymptotes remain the same, but the graph locations change when we apply that -2 and multiply it by the entire function. So this is what our final result should look like. And I know some teachers prefer you to label some points, so I'll do that as well for you guys too, to help a little bit. So this point right here, we know that would be 0. Actually, hang on, this should be 0, -2 because we're multiplying everything by 2. So then I'm going to just change that really quick. Whoa. Here, I think I want to use a smaller pen size. Zero, 2, and 0, -2. And we don't need that part anymore. And I need to redraw the part that got erased. All right. So then another point we have would be 3, 2. Sorry about that. That was another phone call. Usually I am not this popular. I don't know what happened. So I forgot to change the asymptotes. So when we multiplied by, we did the pi x, we just forgot to divide that by 3. So when we apply the 1/3 to the inside of this parent function, or just the function, not the parent function, excuse me, whenever we apply this 1/3 to the inside of the function, we changed the vertical asymptotes. So this one is actually going to be at 3/2. And then this other vertical asymptote in the same period is going to occur actually at 9/2. So sorry, I forgot that part. These are the two vertical asymptotes. And then this is what the function itself looks like. I shouldn't keep saying parent function. This isn't the parent function. This is just the function. So this is what our function looks like. And I want to make it look at least a little more accurate, maybe doing something like that, so that it actually looks like it approaches the asymptote. And then something like this to make it clear that it actually doesn't cross the asymptote at all, because it's definitely not supposed to do that. Alrighty, and then like I said, I do want to label a few points, because sometimes teachers ask us for those points to make it clear if we know where function behavior occurs. So this is going to be at 3, 2. And then if this point right here is 0, -2, then this one over here is going to be at 6, -2, because 6 is going to be our period. And remember that a period is just the amount of x values it takes to execute a full cycle. So a full cycle would be all the way down, down a little bit more, all the way up, and then this right here, 6, -2, would end our first period. And then you could continue if you wanted to, but most math teachers would have you just draw one period and then they'd be good with that. So that's how you draw one period of this function. On to the next problem. All right, so this is the next problem we're going to do in this video. They're asking us to verify an identity. So let's just have kind of a refresher on what identities are. So trig identities are certain equations that establish congruence. They establish equality between one quantity and another. So a really common example of a trig identity would be this one. Sine squared x plus cosine squared x equals 1. So it just establishes for a fact that this thing that occurs on the left is equal to this thing that occurs on the right. So this one is already proven to be true. And then this one, we want to prove that this is true to yet another statement. That would be 2 times cosine squared x minus 1. And as far as I know, there is not a Mac keyboard shortcut for exponents, so I'm going to just use the pen tool to write the little 2 right there. So like I was saying before, this one is already proven to be true. This is one that we use constantly in many, many different areas of math and physics, etc. We're trying to see if we can prove this one using identities that have already been proven true. Like, for example, we could use this one right here to help us prove this one we're given. So that's what they mean by verify. Verify is just another way of saying prove the identity, prove that this is true. So a really effective strategy you can use in a problem like this is to just keep modifying the left-hand side and then eventually see if you can get what appears on the right. So we want to leave the right-hand side alone. We don't want to do anything with this right here. We're going to keep changing the left-hand side and keep modifying it until we eventually arrive at what we have on the right. We want to make sure that we have this appearing on both sides. So let's get started. I'll admit this one is pretty tricky. I was kind of stumped at first. I had no idea what to do, but I've had a bit of an epiphany lately about what to do here. So on the top, this is something that a lot of people don't think about doing. Most people, when they dive into a problem like this, they're in the mindset of trig. They're thinking about all those trig identities. But the thing we want to do first is actually simple algebra, nothing related to trig in particular. So on top, we have something squared minus something squared. So that's a big indication that we want to do what we call a difference of squares. And I want to show you guys maybe remind you what a difference of squares looks like. So this is a really, really special factoring situation. Whenever we have something squared minus something squared, like in this case, we have a squared minus b squared. Another way we could write that would be like this: a minus b times a plus b. So that's how we factor a difference of squares. We're going to do something similar for what we have in the top of this. So we have, instead of a, we have cotangent of x. Instead of b, we have tangent of x. So I'm going to write that as cotangent of x minus tangent of x. And then we're going to multiply that by the other part of the factoring, which turns into a plus b would be cotangent of x plus tangent of x. And we're only modifying the left for now. We're going to leave the right alone. All right, so far so good. So I want to take the denominator and then see if there's a way we can rewrite this so that we can simplify it further. So instead of cotangent of x plus tangent of x squared, I'm going to write it longhand. So I'm going to write it like this. Times itself. To be honest, I'm surprised my handwriting is this good considering I'm using a mouse right now. I'm really impressed with myself, to be honest with you. All right, so what we want to do now is we want to see if there's anything that can be factored out of the top and the bottom. So I see something right away. So we have a cotangent of x plus tangent of x right there. I'm going to cancel it with this one. So let's see what we have left. So what we have left over is going to be cotangent of x minus tangent of x over cotangent of x plus tangent of x. So let's go ahead and simplify this a little bit. So it would be a really good strategy to put everything in terms of sine and cosine. So for example, cotangent of x, we can use the quotient identity and write that as being cosine of x over sine of x. And then tangent would be the reciprocal. So minus tangent of x would turn into minus the reciprocal of this. So instead of cosine of x over sine of x, the reciprocal would be sine of x over cosine of x. And then we're actually going to do the exact same thing on the bottom. So we have basically the same exact thing we have at the top, except we have a plus instead of a minus. So I'm going to just copy the top and replace the minus with a plus. So now things get kind of nasty. We have a fraction within a fraction within a fraction. So what we want to do now is we want to find a common denominator on the top and on the bottom to help simplify things a lot. So in the top, I want to have a common denominator of sine of x cosine of x. So I'm looking at this denominator and I'm looking at this denominator. So our first fraction is missing cosine in the denominator. The second fraction is missing sine in the denominator. So in order to respond to that, I'm going to multiply this first fraction by cosine of x by cosine of x because that's what we're missing in the denominator. All right, and then we're going to do the exact same thing on the bottom. So our first fraction on the bottom is missing a cosine of x in the denominator. So I'm going to multiply the top and the bottom both by cosine of x. And then the same thing applies to the second fraction. I'm going to multiply it this time by sine of x over sine of x because that's what the denominator is missing. I like how as soon as I bragged about my handwriting being good, it just gets worse and worse. Maybe I shouldn't be so boastful. So we have a common denominator now in the top and in the bottom. So on top, we're going to have cosine squared x minus sine squared x. Clearly, bragging about my handwriting was not a good idea. And then the denominator is going to be cosine of x over sine of x. No, not over, just sine of x cosine of x. all over. And then we're going to have the same thing we have here, except instead of the minus, we're going to have a plus, but everything else will remain the same. So we're going to have cosine squared x plus sine squared x. All over sine of x cosine of x. All right, so now that we have a fraction on top of another fraction and both fractions have the same denominator, there are laws of fractions that tell us that we can cancel things like this. So this is equivalent to that. They both go away. And what that means for us is that we have just one single fraction, one simple fraction. I'm going to write that right now. Our result is going to be cosine squared x minus sine squared x over, and remember at the beginning of this problem, I wrote an example of a trig identity. I wrote the identity that tells us that sine squared x plus cosine squared x is equal to 1. So I'm going to use that same exact identity to help us with this next part. So this in the red box is just 1. It's the Pythagorean identity that tells us the value of everything in the red box is just simply going to be 1. So we're going to have all of this over 1. So you don't even really need to put the 1 there. I'm just putting it there to make a point. So our result should be this. But notice how we're not quite where we want to be yet. We want to be at this point right here. What we have is just that. So we're getting closer. We have to do a little bit more work, but we're really, really, really close. So let's think about a way to do this. So I think we might want to use the same identity again. So I'm going to manipulate it this time, and I'm going to type it. So we have sine squared x. I'm going to put the square a little bit later. We have sine squared x plus cosine squared x equals 1. So we want to have things in terms of cosine. If we look at what we have on the right-hand side, we have something in terms of cosine. So I want to transform the sine into cosine. I want to put the sine in terms of cosine. So I'm going to subtract cosine squared x on both sides in order to accomplish that goal. On the right side and now on the left. So then what do we get as a result? Well, we get sine squared x equals 1 minus cosine squared x. So what I want to do now is I want to take this entire sine squared x. I want to replace that with cosine 1. I want to replace it with 1 minus cosine squared x. So let's simplify. We don't have to put the 1 there again. It's just going to be a simple expression with no denominators, no fractions whatsoever. So I'm going to simplify this. We have to start by distributing the negative. So this is going to turn into minus 1, and then we're going to have a plus cosine squared x after we distribute. So let's simplify things a little bit. So cosine squared x plus cosine squared x, that turns into 2 cosine squared x. And then we have the minus 1. All right, perfect. So we have exactly what we're looking for. I mean, the only difference would be not having the parentheses, but with or without the parentheses, it has no effect on the ultimate value. So we've successfully verified this identity. All right, so let's do one more problem now. So we have a bit of a geometry problem to do right now, and I forgot to type something. Leave your answer in terms of the trig functions. So ultimately, we're trying to find the area. So let's talk about how to do that real quick. But before we even get into that, I want to just draw the picture. So it's a 9-sided polygon, otherwise known as a nonagon, and those are not easy to draw at all. So I have a little trick to help me accurately draw these things. So we know that a circle has 360 degrees. In order to figure out where I should make the vertices of the polygon, I'm going to do 360 divided by the number of vertices, which is 9. So 360 divided by 9 is 40. So I'm going to put a vertex right there. And then if we have a center right around there, this is approximately going to be, if this is about 90, this is going to be 45. Then 40 would be just slightly less than 45. So our next vertex should be right around here. So then this right here is a 40-degree angle. Just like that. So we should have 9 40-degree angles in order to get an accurate depiction of this. Whoops. So we're going to do another 40. So far we have 2 sides. We should have 9 by the time we're finished. So we have 2 40s, and then another, and then another, and then another. And this is going to turn out horrible, just a fair warning, but it should look something like this. Clearly, I graduated at the top of my class in art school. So it does not look like it's inscribed, so I'm just going to do a quick fix to make it inscribed. So remember that the definition for something to be inscribed means that all the vertices of the polygon have to touch the outer edge of the circle. So we have some vertices that are not on the circle itself, and that is a problem. So that's why I'm doing this fix right now. So it has to actually touch the circle for it to be considered inscribed. So how the heck do we even find the area of this thing? So we're going to need to split it up into some triangles. So this is the center of our circle, and it's also the center of the polygon. So we're going to split it up into some triangles. Imagine we're making circles. Imagine we're making triangles all the way around. So just imagine we're doing that. I'm not really going to do that, but just picture that in your mind. And the reason why that's an important step is because if we can find out the area of one single triangle, we can just multiply that by 9 to get the area of the entire polygon, which is exactly what we want. So let's see if we can find the area of this triangle that I drew. So we're going to need some things to help us out here. So I think what I'm going to do is I'm going to draw this triangle by itself off to the side. So it's going to look like this. This is our triangle. This triangle has an area of capital A. So how do we find the area of a triangle? We need 1/2 base times height. So it's important to note that it won't be the slant height. So this can't be our height. It's going to have to be the straight up and down height only. So we don't have any of that information to help us. The only thing we have would be the fact that our radius, so if the radius of the circle is 3, that means this side length is 3, and this other side length is also going to be 3, which correspond to this side and this side on the triangle off to the side. So it doesn't look like it will help us that much, but it actually helps us out quite a bit. Because what I'm going to do now is I'm going to draw half of the triangle. So here we have half of the triangle. The 3 is still going to be a 3. The height's still going to be a height, but the B is going to be cut in half. So what information do we have to help us with this? Well, we know that this angle right here has to be 40 degrees because 360 divided by 9 gets us 40. So this is a 40-degree angle, and I'm going to do my best to write it without screwing up. So then let's see if we can use some trigonometry knowledge to help us put these in terms of the trig function of 40 degrees. So let's start with B. So if we look at B relative to our 40-degree angle, and if we look at 3 relative to the 40-degree angle, B is opposite the 40, and then 3 is the hypotenuse. We have an opposite, and we have a hypotenuse. So if we think of SOHCAHTOA, this is going to be sine. So sine of 40 degrees is opposite over hypotenuse. That means that sine of 40 degrees would be b over 3, because b is the opposite of the angle, and then 3 would be the hypotenuse of the angle. Which means if we were to just solve for b, b would be 3 times the sine of 40. I'm going to make a modification here. So then we're going to do something similar for h, for the height of the triangle. This time we have the adjacent and the hypotenuse. So we're going to be using cosine for this, because that would be the CAH part of SOHCAHTOA. Cosine is adjacent over hypotenuse. Cosine of 40 degrees would be h over 3. And then I'm going to make a modification similar to what I did above with the sine function. I'm going to make this into 3 cosine of 40 is h, and we get that by multiplying both sides of the equation by 3. All right, so I think we have enough information to find the area of this triangle. So let's go ahead and apply it to the top one. So if this is our first, if this is b right here, b corresponds to this part, I'm actually going to double this right now to get this top b. So this applies to the bottom triangle. I'm going to double everything to get it to apply to the top. So if this b down below is 3 sine 40, then this b above is going to be 6 times sine of 40. So this would be the entire base of this top triangle, 6 times sine of 40. And then after that, we have the height too. The height's going to be 3 cosine of 40. That is our height. So now we want to find the area of the triangle, now that we have the base and we have the height. So area of a triangle is going to be 1/2 base times height. 1/2 base, which is 6 times sine 40. Times the height, which is going to be 3 times sine of 40. Oh, sorry, 3 times cosine of 40 is what I meant to say. So let's simplify a little bit. So 1/2 times 6 is 3. And then 3 times 3 is 9. So ultimately, our coefficient should just be 9. So that means our area is going to be, that's not an A, not even close. So our area is going to be 9 sine of 40 times cosine of 40. So what does this correspond to? So this is going to be the area of one triangle. So I'm going to outline this in green. So this right here is the area of the green section of the triangle. So that means to find the area of the entire polygon, which is this right here, finding the area of this polygon, all we need to do is multiply A by the number of triangles we have altogether. So we have, typically we use n to denote the number of sides or the number of vertices in a polygon. So in this case, n is 9. It's a nonagon, so n is 9. So we're going to do 9 times this expression. We're going to do 9 times the area of one triangle to get the entire area of the polygon, the entire area of the nonagon. So if we do 9 times A, we get 81 sine of 40 degrees times cosine of 40 degrees. So our area, I'm going to change things up a little bit. I'm going to call this capital A, which is now going to refer to the entire polygon and not just one triangle. So this is the area of the polygon in terms of trig functions.